I want to talk about the physics concept of work. The concept of work in physics is a very, very important concept. But Chantel, one of the issues is we confuse the physics concept with the English word. When someone says they're doing work in English, what they usually mean is they're getting tired. Tiredness is not work. Okay, tiredness is something else, and I'll show you what we mean by tiredness in physics. But in physics, work has a very specific meaning. It is not doing something that makes you get tired. Instead, you do work on an object. Okay? I see a number of you looking at your calculators almost as though you're working on the study guide and not paying attention. That would be foolish. If work is to be done on an object, two things must happen. Number one, a force has to be acting on the object, an unbalanced force. And number two, I take that back. It doesn't have to be an unbalanced force. A force has to be acting on the object. And number two, the object must move through a distance, and here's the key, in the same direction as the force. If work is done on an object, Ethan, the force and the distance have to be in the same direction. Work is a scalar, and it's calculated by, symbol we use is capital W, which also is the abbreviation for watts and for west. Have I mentioned that we're running out of letters in the English alphabet? We don't have enough to go around, but we'll have to make do. And it's calculated by force times distance. Because it's a scalar, I didn't put the vector sign on the force, even though force is a vector. But we do have to always check to make sure that the force and the distance are in the same direction. What would the units be? We measure distance. It's a Newton meter. But this is so important, we've given this a special name. We call a Newton meter a joule, capital J, named after a scientist whose last name was Joule. There is one more condition. In this equation, the force has to be constant. It can't be a changing force. You can't push harder or lighter on an object and use this equation. You can still calculate work, but typically then you need some kind of a calculus workaround. Okay? Example 1, I like example 1, I like example 1. Example 1 is a nice question. Neha, what's example 1 asking me to find? How much what? The third word after the word much. How much what? Sorry, I said Neha. Wow, wrong name. Got the N name correct. That was terrible. Sorry. How much work? Right? Okay, let's try that again. Boy, did I butcher that. Nuji, I said Neha. I'm sorry. Brain is in two different locations. I had the N and then my brain went elsewhere. Nuji, what's this question asking me to find? How much what? Work. Okay? So, do me a favor. Everybody write down work equals force times distance. Oh, can you look and see where that is on our formula sheet so that you know what section we're going to be in for the next little while? Okay. I think it's about, 2/3 of the way down-ish? On the front page, half of the way down on the front page? Okay. Everybody right now, there's a trigger word here. Can you all underline the word lift? Okay. I'm going to get really technical for a little bit, and then we're just going to relax. Over here, I'm going to do a free body diagram. Put a little dot. Let's assume you're lifting something, and you're lifting it at a constant speed. You're not accelerating it. What are the forces acting on this object? Get the obvious one. Gravity. Okay. And then you would have force lift. I'm going to abbreviate that as FL. So this is technically FL times distance. I don't know FL. Oh, but look. I know another force that has to be the same size as FL. from my free body diagram, which one has to be the same size. Because I said we're lifting at a constant speed. We're not doing extra work. We're doing bare minimum work. And so I can write this as mg, and what we typically write instead of distance to let you know we've gone to scalarville, h for height. And I did this song and dance because, Riley, I just finished telling you that the force and the distance have to be in the same direction. When you're lifting up. What direction is gravity? Up? But what I'm arguing is not that the force pointing up is gravity. I'm arguing, look, it's the same size as gravity. It's F lift, but we're just going to say it's the same size as gravity, so we can substitute an mg in there. But again, Jake, I'm being very cautious and saying, yeah, I'm not saying that the force gravity is up. The lift force is up, but it happens to be the same size as gravity. Jake, what is the mass in this question? G, you've probably memorized G. How big is... Yeah, and we're in scalarville, so not negative. Height, 9.5 meters. What do you get? You get 1,117, I'll call it 1,120 units. Joules. Direction. It's a scalar. No, it's a scalar. No direction. Much like your cube. Yeah, it's a scalar. Okay. Is that a lot of work? Well, 9.5 meters is about roughly 3 flights of stairs. 12 kilograms, about 25 pounds. So around the order of maybe a bucket of water. All of you could do that. Now, if I asked you to do that over and over and over and over and over, okay, that's a different story. But all of you, if you had to, could carry a bucket of water up 3 flights of stairs. Most of you would complain because you're teenagers, but you could do it. So 1,000 joules is not very much work. We can do it pretty casually. Instead of coal, let's use Julian. Julian, could you stand up for me, please? And over there's a blank spot on the wall. Could you go push as hard as you can on the wall, please? I'm serious. Push. Harder. Put your back into it. Okay? If I made Julian, just pretend you are now. Mime it. Push. But just pretend. If I made Julian do that for an hour, would he get tired? Okay? Is tiredness, keep doing it, the same as work? Okay. Is he doing any work? Why not? No distance. Okay? This is why I had to say to you, work has a very specific meaning in physics. You can sit down, Julian. So how much work has he done? Nothing. Was he applying a force? Yes. Was there a distance? No. Pause the video for a second. Example 3. Pushing a box along the floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Quick check. Are the force and the distance in the same direction in this question? They are? Okay. Work equals force times distance. This one is straight plug and chug. Nick, how big is the force? What distance? How much work? (306 joules). And what we would also say is this, Nick, in doing this work, your body lost 306 joules of energy and the box gained 306 joules of energy. And we'll talk more about how that works over the next few days, but it's another way to think about it. partly answering your question, because work is a scalar and doesn't care about direction, that actually, believe it or not, dominates your life in ways you can't imagine. Dylan pedals his bike up a 19-meter high hill that is 91.4 meters long. The combined mass of the bike and the rider is 65 kilograms, and the bike requires a steady force to continue up the hill. First question. Suppose instead of biking up the hill, suppose we had a rope dangling and Dylan strapped the bike to his back and carried himself and the bike up the rope. How much work would he do if he climbed the rope? That's a good question. Let's write down W equals force times distance. You know what? I'm going to argue that if he was climbing straight up the back of the hill with the rope, he's lifting himself. Lifting himself. This is going to be the force done by lifting times distance. Who remembers what was the force when you were lifting something the same size as? In fact, this is going to be mgh. It's going to be 65 times 9.8 times 19 I get 12,103. Write down all the sig figs because we're going to use this. 12,103 joules. Is that right? How much force is he going to use? Well, 65 times 9.8. He's going to need to exert 637 newtons of force. What if he can't? But he still needs to do 12,103 joules of work. Well, all a hill is, it's a force multiplier. What we actually say is this. Instead of going 19 meters and needing 637 newtons of force, we can increase the distance, and if we increase the distance, you don't need as much force. You're still going to do the same amount of work. So how much work will Dylan do riding his bike up the hill? It's still going to be 12,103 joules. Now, why is that? Alisher, this partly answers your question. Work is a scalar, and so it doesn't care if you, suppose you need to get from here to here. It doesn't care if you go like that, or if you go like that, or even if you go like that. It does not care about the path that you took to get there. All it cares about is the work that you did. And so going this way and this way, no work in this direction because gravity is in the opposite direction of the distance. All the work in this direction, 12,103 joules. You can also do 12,103 joules this way. Which one has a bigger distance? The obvious, going up the hill or climbing the back of the hill. Which one has a bigger distance? Which one requires a smaller force? Going up the hill. By lengthening the distance, you can decrease the force. And that's what we call a simple machine. A simple machine is a device that reduces the force required, Daniel, to get the same amount of work. And we use them all over the place. Levers are simple machines, pulleys. I think there's 5 simple machines, and I've forgotten them. I can't rattle them off the top of my head. But let me give you an example. Turning a screw with your fingers is very, very difficult. Why is turning a screw with your fingers very, very difficult? Well, because the screw head is such a tiny distance, you need a massive force from your fingers. Or you can use a screwdriver. The screwdriver has a much larger distance if I were to stretch that line out, which means what? Don't need anywhere near the force to turn that screw. That's all a screwdriver does. It's a force multiplier. You have to do the same amount of force times distance work to get the screw in, but by having a larger radius, you're going to end up turning your hand in a larger distance, way less force required. Way less force required. Or, if you're not trying to screw something, it's what a wrench does as well if you're trying to undo a bolt. So if you have a bolt, you can try turning it with your fingers. That's going to be a very, very small distance. It's going to require a massive force. Or, you can put a wrench on it, and now you'll turn it through a massive arc, a huge distance, tiny force required. Same amount of work. This shows up when you start to look for it, Alisher. You're going to stay awake. Your blinks are getting longer and longer all over the place. You'll time and time again, especially if you're doing any kind of a trade, any kind of a physical task, you'll realize, oh, that's what stairs are. We could have all of our stairs vertical, but that would require you to exert mg to get to the next floor. What do we do instead? We put them at an angle, we increase the distance, and you don't even notice the force required to go up the stairs. You can casually carry on a conversation while going up the stairs. We've reduced the force, but I'm telling you, you're doing the same amount of work. So, what was mg? mg was equal to 637 newtons, which is a fair bit of force. How much force does Dylan need to pedal up the hill? Well, now we could go like this. Work equals force times distance. Caden, what's C asking me to find? Get the force by itself. Yet another equation for force that I'm not going to bother memorizing it. I'll derive it when I need it. When will I need it? Well, if I know how much work and if there's a distance. So this is not MA, but it must work out to the same thing somewhere along the way. Yeah, F is going to be work divided by distance. The work was 12,103. Pedaling up the hill, what was the distance? How many meters, Caden? 132 newtons. Significantly less. The ramp is one of the great simple machines. It's the ramp, it's the lever, it's the wedge, it's the pulley, and I think it's the screw. I think those are the 5 simple machines. And all of them increase the distance required to do a task of work, but yet they make it so that you need way less force. For example, the Egyptians, to build the pyramids, they just used ramps. Very, very shallow ramps, and that was enough for them, instead of having to lift the blocks against gravity, just sliding it forward, making it a smaller ratio even than that. Works fine. Okay. So, this is one of the nice characteristics about work. Turn the page. It's a scalar. So example 5 asks, how much work would it take for Dylan to ride to the top of this hill? It's the same question as before, because the final height is 19 meters. See it over here? It's going to be 12,000. You know what? We could even go like this. It's going to be mgh again. It's going to be 12,103 joules. How many of you have been to Science World, and there's a little chair that you can sit in with a rope pulley where you can lift yourself up, and one of them is way easier and one of them is way tougher, okay? The tougher one, you're pretty much lifting your own, actually I think they've cut gravity in half. The easier one, the rope connects to the pulley numerous times. I was there over the Christmas break with my niece. There's 6 rope connections. So to raise yourself 1 meter off the ground, you have to pull 6 meters of rope through the system, but you're only having to lift 1/6 of your weight. In the other one, to raise yourself 1 meter off the ground, you have to pull 2 meters of rope through the system, and you're having to lift half of your weight. And that's why one of them is way easier, but you don't move as fast. The other one, you move faster, but you got to pull way harder. Pulleys. Amazing inventions. Great physics. Hey, what takes more work? Lifting a 25 kilogram mass to a height of 4 meters or lifting a 50 kilogram sack to a height of 2 meters? Presley, what do you think? What? What? How so? Because if you go MGH, you'll get the same answer for both. Really, the M times H works out to the same, and the G is not put. Yeah, they are the same. They are the same. Okay. We're going to ask on Wednesday, what if the force isn't constant? What if it's changing? And we'll have to come up with a workaround. No pun intended.